Hello everyone, this is Evan Moon. I'm working together with GEL Sub on Thailand market for cosmetic raw materials. Today I'm explaining the gel stabilizer to use of hectorite clay materials for emulsion and dispersion systems. This slide explains the functional role of three different raw materials that interact with the distilled hectorite, forming stable dispersion in the oil phase. These materials are key to achieving excellent texture, stability, and viscosity control in cosmetic formulation that use light and volatile oils. The first material is isododecane, which is dispersed into the ammonium hectorite. Isododecane is widely used as a cosmetic ingredient because of its lightweight feeling and dry touch finish. It enhances the spreadability and the texture without clogging pores or causing acne. Its matte finish effect is particularly favored in the makeup product. Chemically, isododecane is a branched hydrocarbon. The second ingredient is cyclopentasiloxane. It's a volatile silicone, also dispersed into ammonium hectorite. Cyclopentasiloxane is a clear, odorless, and fast evaporating silicone. Its right textures and lubricating properties make it ideal for product that's quick drying, such as antiperspirant primers and hairspray. It gives silky finish on the skin and hair and evaporate quickly without leaving residue. Last materials, capryl triglyceride, is an ester oils or dispersed into the ammonium hectorite. This ingredient is already known for the smooth and lightweight and textures that lock in the moisture without the grease shininess. It's used in lipstick, eyeliner, and moisturizers. Besides being the skin emollient, and it also acts as an antioxidant and provides oil phase dispersion stability, improve viscosity and consistency. Oil phase dispersion stabilities improve viscosity and consistency, and help protect the formulation from oxidation. All kinds of three materials, oils, isododecane, cyclopentasiloxane, and capryl triglyceride, when dispersed into the distilled ammonium hectorite, forms a stable gas and with a card-house structure. Using the propylene carbonate as an activator, the layers hectorite as well and exfoliate, allow the edge-to-phase interaction that build a three-dimensional network. These structures enhance the viscosity and stabilize the oil phase and support the production of elegant and high-performance cosmetic texture, such as a balm, a stick, and emulsion-free product. This slide images highlight the benefit of using the GELs in the cosmetic formulation, particularly for emulsion and stick type of product. GELs provide non-tacky and non-greasy textures, making the product feel light and comfortable on the skin. It enhances the ease of application and allows for smooth, even spreading of the product. One of its key advantages is uniform distribution of pigment, which help achieve a natural and flawless finish. In water in oil and water in silicone emulsion like BB cream and cushion foundation, Its GEL contributes to improved emulsion stability and enables cold process formulation, save both time and energy during the manufacturing. In-stick, pop product, and pencil for lip and eye. It maintains homogeneity throughout the product, prevent oil separation and pigment bleeding, and support one-swipe application. And its gels is a powerful multifunctional ingredient for both sensory improvement and formulation stability in modern cosmetics. This slide is explain the classification layers of silica minerals related to clay minerals. Clay minerals belong to the phyllosilicate families, a broader group of silicate minerals. These families include both large, well-known true mica, such as muscovite and biotite, as well as brittle mica like margarite, and which is a calcium-rich mica with a formulation calcium aluminum and then hydroxide consist. Our understanding of clay minerals largely come from studying this mica at a macroscopic level. As they are well-defined, crystal structures serve as useful models for interpreting more complex and smaller scales clay structure. Among the key types of clay minerals and smectite, which include montmorillonite, badellite, nontrinite, and hectorite, these are classified to one-rayed clay minerals, meaning they consist of two tetrahedral silica sheets and sandwiching one octahedral sheet. Smectite forms through the weathering of rocks of bentonite or volcanic ash, and part of the hydroxyl aluminous silicate group, making them highly reactive and important of both geological and industrial context. This chart is explained the structural and classification common clay minerals, kaolin, illite, and marmorinite like smectite. Kaolinite has a one layer structure with a strong hydrogen bonding between the layers, making a non-swelling and stable. Illite has a 2-1 structure with the potassium ions acting as bridges between layers. This result is moderate bonding strength and also no swelling. Like kaolinite, it has a negative charge due to same type of silica and aluminum ions substitution. Last one is the marmorilonite, like a smectite and hectorite part groups, also has a 2-1 structure, but allows us water and various positive ions, natrium and calcium cation between the layers, giving it weak bonding and high swelling capability. And the octahedral form substitutions include aluminum and ferric cation, while in the 3 octahedral forms, hectorite is magnesium and lithium ions are involved. This slide explains 3 important types of layered clay minerals above explained the slide. And kaolinite is muscovite and smectite. First, kaolinite has a 1 layer structure composed of silica tetrahedral layer and 1 alumina octahedral layers. These layers are bonding tightly by hydrogen bondings, which prevent waters or ions from entering the interlayers. Because the Kaolin has a non-swelling clay, very low cation exchange capacity. Next, muscovite and 2,1 layer minerals consist of two silica tetrahedral layers surrounding one alumina octahedral layer. The interlayer spheres are filled with fixed potassium ions that keep the layer. As a result, muscovite is also non-swelling, and lastly is explained as smectite as monomorillite like hectorite. They has a 2,1 structure similar to muscovite, but with a key difference is interlayer contains exchangeable cation and water molecules. This cation can easily be replaced and water can enter the interlayer, causing the structure to swell very well. This makes the smectite high swelling clay and a very high cation content. This slide explains the electric double layers in clay minerals, hectorite and bentonite. It is explained the clay mineral like hectorite and bentonite carries a negative surface charge, mainly due to isomorphic substitution within their crystal lattice. When these clays are immersed in water, an important process called cation exchange occurs. Cations such as calcium, magnesium, natrium, and kalium are attracted to the negatively charged clay surface. These positive ions create a location region of a high cation concentration around the clay particle. Next, water molecules which have a dipole structure attract to these cations. This form the layers water structure called electric double layers. This slide introduced the stellodiumunium hectorite. It's an organic modified clay derived from hectorite. Smectite types of layered silicate. It is a natural stable. Hectorite contains the sodium or other cation in its interlayer spheres. These are replaced with these stellodiumunium ions, which are quaternary ammonium compound featuring two long steric chains. This modification makes clays hydrophobic and highly compatible with oil and esters, allow it to function effectively in anhydrous and oil-based cosmetic formulation. One of the most important roles is the ability to form a three-dimensional card house gas structure. When used this with a propylene carbonate polar solvent, this solvent interactions into the clay layers, weakening the electrostatic pores and exporting the layers. This slide shows hectorite forms a stable water in oil emulsion by hydrogen bonding between clay plate and water molecule. Using oil activator and water created a card house structure that trap oil droplet, lead to a stable suspension. These tables compare the oil galling efficiencies across different oil flowings of various in the gel formation, depending on the oil type. This slide is edge to face and face to face activation. First, the edge to face activation is positively charged. The edges are attracted to a negatively charged face forming card house network via electrostatics interaction. Second is face-to-face interaction is a negatively charged surface around in the parallel and aggregated through van der Waals force or reduced repulsion, leading to circulation. These diagrams illustrate isotherms and manufacturing process, which involve the dispersion hectorite and the oil paste. First, the mixture of hydrocarbon or silicone or ester oils and press in the mixing vessel. Under continuous stirring, and then hectorite powders is slowly added in the oil paste. As mixing continuously and uniform, and clay begins to swell and disperse throughout the medium in the next step, an activator, such as propylene carbonate is introduced. This helps exfoliate the layer's clay structure and initiate the formulation of the three-dimensional card house gel network. After full activation, the mixture is allowed to rest or undergo homogenization, resulting in the smooth and stable gel structure. These gels provide excellent thickening, suspension, and stability for cosmetic formulation, such as balm, stick, emulsion, and emulsion-free systems. Thank you very much. My presentation attention, and see you next time.